Welcome back, everyone. I am so thrilled you're joining us for this explainer. Okay, today we're tackling a truly wild problem, straight from the world of atomic physics. Picture this for a second. You are tasked with stopping a projectile, but this isn't just any projectile. It's incredibly tiny, it carries immense energy, and here's the kicker, it has absolutely no electrical charge. Because it has no charge, it completely ignores the magnetic or electrical fields we'd normally use to slow things down. It literally just zips straight through most matter like a ghost. We're talking, of course, about a fast neutron. So, how in the world do you control, let alone completely stop, an insanely fast, totally invisible bullet?
So how do you slow down an invisible bullet? That's the central mystery we are going to unravel today. Think of the fast neutron as our unruly protagonist. It's born out of a nuclear reaction, just flying out at blistering, chaotic speeds. But for nuclear technology to actually work for us to harness that incredible energy safely and consistently, we need this protagonist to chill out. We need it to lose its energy and slow down to a very specific, manageable pace. But if it just phases right through most materials, what could we possibly put in its path to hit the brakes?
Okay, let's dive into this. The solution actually lies in a physical concept known as neutron elastic scattering. Now, I know elastic scattering sounds super intimidating, but trust me, you've probably seen it 100 times. Just picture a game of pool. When a fast-moving cue ball smashes directly into a stationary target ball and they bounce off each other without breaking apart or generating a bunch of heat, well, that's an elastic collision. In the subatomic world, when our fast neutron strikes an atomic nucleus without exciting that nucleus, so just pure kinetic bouncing, it behaves exactly like those two billiard balls colliding on a table.
To crack the case of how to stop this neutron, we just need to understand the language of the crash. And it basically boils down to three simple building blocks. First up, we have E, which is our incident energy. That's simply the amount of energy our fast neutron has right before the crash. Next is E prime, the scattered energy. This is whatever energy the neutron happens to be left with after it bounces off the target. And finally, we have a very special collision parameter called alpha. You can think of alpha as the fraction that dictates the absolute maximum energy our neutron can lose in a single head-on collision.
In the math here, it's beautifully simple. To calculate alpha, the formula is just a minus 1 divided by a plus 1 entirely squared. But what's a? Well, a simply represents the mass number of our target nucleus. In everyday terms, a is exactly how heavy the obstacle is that we're putting directly in front of our invisible bullet. The math here is incredibly elegant because it tells us that the exact amount of energy the neutron is going to lose depends entirely on the weight of the target.
So let's look at what happens in a perfect head-on collision, the kind where the neutron hits the target dead center. This first equation shows us that the absolute minimum energy the neutron can be left with, E prime, is simply alpha multiplied by its starting energy, E. So, if we want to find out the maximum energy the neutron lost to the target, we just do a little simple subtraction. We take the starting energy E minus the leftover energy E prime. This leaves us with E times 1 minus alpha. It's a gorgeous mathematical proof that shows us exactly how much energy gets transferred from the neutron to the obstacle during that crash.
And that brings us to this absolutely incredible, revealing statement from our source material. When A is close to 1, the neutron loses almost its entire energy. I really want you to think about that for a second. The secret to stopping our high-speed, invisible projectile isn't about building some massive, impenetrable fortress. It's actually about finding an obstacle whose mass, our A value, is as close to the number 1 as possible.
To truly grasp how perfectly this works, let's pit two extreme opposites against each other. In the lightweight corner, we have hydrogen. Hydrogen is literally the lightest element in the universe. Its nucleus is essentially just a single proton, giving it a mass number of exactly A equals 1. In the heavyweight corner, let's look at a champion like uranium. Uranium is a massive, dense element with a whopping mass number of A equals 238. So which of these makes the better brake pad for our neutron? Let's test them out.
Now, what's really interesting about this slide is how the math just magically unfolds when we use hydrogen. Remember our alpha formula? Okay, let's plug in a 1 for hydrogen's mass. We get 1 minus 1 over 1 plus 1. Well, 1 minus 1 is 0, and 0 divided by 2 is, obviously, still 0. 0 squared? You guessed it, 0. The math cleanly, elegantly, and completely cancels out.
Boom, 0. Alpha is exactly 0. And because alpha is 0, the scattered energy,
Our E prime is 0 multiplied by the initial energy. The result is an absolute staggering 0. So what does this mean in the real world? It means that when a fast neutron collides head-on with a hydrogen nucleus, the neutron transfers 100% of its energy to the hydrogen. Our fast, invisible bullet completely stops.
Think of it kind of like a table tennis impact. If you've ever rolled a ping pong ball straight into another stationary ping pong ball of the exact same size and weight, you know exactly what happens. The first ball hits the second and instantly stops dead in its tracks. All of its kinetic energy is instantly transferred to that second ball, which shoots forward across the table. Because a neutron and a hydrogen nucleus have almost the exact same mass, this perfect energy transfer happens right down at the subatomic level.
Let's move to the other end of the spectrum and see how this builds when we switch to our heavy extreme, uranium, with its massive weight of 238. If we plug 238 into our formula, we get 238 minus 1, divided by 238 plus 1. That's 237 divided by 239 squared. When you crunch those numbers, alpha comes out to approximately 0.98. Now, that is a huge difference from the pure 0 we just got with hydrogen.
So, because alpha is 0.98, our resulting scattered energy, E prime, is 0.98 times E. This means that after a direct head-on collision with a gigantic uranium nucleus, the neutron walks away keeping 98% of its original speed and energy. It basically didn't even notice the crash.
2%. Just 2%. That is the frustrating, totally counterintuitive reality of atomic physics. A massive, incredibly dense element like uranium only absorbs a pathetic 2% of the neutron's energy during a collision. So if your goal is to slow down a neutron, heavy metals are utterly, completely useless.
To really visualize why, imagine taking a super bouncy ball and hurling it as hard as you can against a solid, heavy brick wall. The wall is so massive compared to the ball that it doesn't absorb any of the kinetic energy to move itself. Instead, the ball just violently ricochets off the bricks and bounces right back at you at nearly full speed. The neutron bouncing off uranium is exactly the same concept. The target is simply too big to take the energy away.
So, the crucial point is this. To control the chaos of nuclear reactions, you don't build heavier walls. You use the lightest elements possible. And guys, this is the ultimate secret of thermonuclear reactors. When fast neutrons are released, engineers surround the core with a moderator, usually ordinary water or heavy water, which are absolutely packed with hydrogen atoms. Because hydrogen's mass is essentially 1, it only takes about 20 of these billiard ball collisions to drain a high-speed neutron of nearly all its energy. That slows it down perfectly to keep the reactor running safely and efficiently.
It really makes you step back and marvel, doesn't it? The ability to safely generate massive amounts of electricity for our cities, our hospitals, and our homes entirely depends on understanding a simple fraction, alpha, and realizing that the best way to catch an invisible bullet isn't with a giant shield, but with a target exactly its own size. Isn't it amazing how mastering the math of tiny, invisible collisions is the secret to powering our entire modern world? Think about that the next time you flip a light switch. Thanks so much for joining me for this explainer, and keep questioning the fascinating world around you.